In this video we're going to investigate the gradient of exponential functions. Now we need to remember something that you'll have met earlier in the course of Unit 1, and that is if we have a curve y equals f of x and we take 2 points on the curve y equals f of x, where P is the point with an x-coordinate of A. So the coordinates of P are the point A, f of A. And Q is the point whose x-coordinate is A plus h. So the y-coordinate of Q will be f of A plus h. Then the gradient of the segment joining P to Q is going to be the y step, which is f of A plus h minus f of A, divided by the x step, which is just h. So the gradient of the segment PQ is f of A plus h minus f of A divided by h. If h is small, so that the point Q is close to the point P, then the gradient of our segment PQ will be very, very close to the gradient of the tangent at P. And the gradient of the tangent is denoted by f dash A. So we can say that if h is small, then f dash A is very close to the value of f of A plus h minus f of A divided by h. So the gradient function f dash x will be very close to the function g given by g of x is f of x plus h minus f of x divided by h, provided h is a small number. So to summarize, we're saying that the gradient function f of dash x is approximately equal to the function g of x given by f of x plus h minus f of x divided by h. And that estimate will be good provided h is a nice small number. So now let's use this with the function f of x being 2 to the power x, and we're going to have h being a nice small number, namely 0.001. So we've got g of x is 2 to the power x plus 0.001 minus 2 to the power x, all divided by 0.001. Now in the video that we've got here, we have got the graph of f of x equals 2 to the power x. And to that graph, we are going to add the gradient estimate curve, which is in blue now. And now we're going to consider the gradient values at different points on the original graph. So at the point 0,1, the gradient is 0.69339. At the point 1, 2, the gradient is 1.38677. At the point 2, 4, the gradient is 2.77355. At the point 3, 8, the gradient is 5.5471. And at the point 4, 16, the gradient is 11.0942. So let's summarize that on the next page and have a look more carefully at the values that we've got. So at the gradient at x equals 1 was 1.38677, which was double the value of the gradient when x was 0. When x is 2, we had the gradient was 2.77355, which is 4 times the value of 0.69339. When x is 3, the gradient of the curve is 5.5471, which is 8 times the gradient when x was 0. And when x is 4, we had the gradient was 11.0942, which is 16 times the gradient when x was 0. Looking at these results a little bit more carefully, 2, 4, 8, 16, of course, just the powers of 2. So we can put in that the gradient at x equals 1 is 0.69339 times 2 to the 1. The gradient at x equals 2 is 0.69339 times 2 squared. The gradient when x equals 3 is 0.69339 times 2 cubed. And the gradient when x equals 4 is 0.69339 times 2 to the power 4. Putting the results together, it looks as if the gradient of the curve y equals 2 to the power x at the point p 2 to the power p is simply 0.69339 times by 2 to the power p. The 0.69339 that we've got there is the gradient of the curve at the point where x equals 0. So we can write, if y equals 2 to the power x, then dy by dx is 0.69339 times by 2 to the x, which is the gradient of the curve at x equals 0 times by 2 to the power x. Alternatively, if we say that f of x is 2 to the power x, then we can say that f dash x, the derivative, the gradient function, is 0.69339 times by 2 to the x, which is the value of the gradient when x equals 0 times by 2 to the power x. Now, we can justify this result algebraically using small chords, and although this is probably extension work, it's worth just seeing how this proof goes. So just recall that we know that we can estimate the gradient of the curve by using our gradient estimate function f of x plus h minus f of x divided by h, where h is a reasonably small value, and that the smaller the value of h, the better the approximation will be. So, if f of x is 2 to the power x, then f dash p is very, very close to the value of g to p, which is 2 to the p plus h, that's f of x plus h, f of p plus h, minus f of p, which is 2 to the p, all divided by h. Now, remember from our rules of indices that 2 to the p plus h is 2 to the p times by 2 to the h. So we can say that f dash p is going to be approximately 2 to the p times 2 to the h minus 2 to the p, all divided by h. The top of the fraction has got a common factor of 2 to the p. So let's take that common factor of 2 to the p out. So we can now say that f dash p is approximately 2 to the h minus 1 divided by h times by 2 to the p. Now at this stage we need to notice that g of nothing is defined to be f of 0 plus h minus f of 0 divided by h. But remembering that f of x is 2 to the power x, then f of h is just going to be 2 to the power h. F of 0 is just going to be 2 to the power 0, which is 1. So g of 0 is going to be 2 to the h, take away 1, divided by h. So we can now write that f dash p is approximately equal to g of 0 times by 2 to the power p. Now, to get an exact value for f dash p, what we need to think about is what happens as we let h get smaller and smaller, so that the approximation becomes better and better. Now, if we let h get smaller and smaller, then the value of g of 0 would get closer and closer to the value of f dash 0. So we can say that f dash p is going to equal f dash 0 times by 2 to the p, or equivalently f dash x is going to equal f dash 0 times 2 to the power x. So the algebra that we've done on this page, which should be regarded as extension work, justifies the statement that we made on the previous page using the patterns we'd seen from GeoGebra. Now, as a final little challenge from this video, here's the graph of y equals 1.5 to the power x and the curve of the gradient estimates using GeoGebra, and the challenge for you is to find a rule for the gradient of this curve. And if you really fancy a big challenge, then you could try and prove that your result is correct algebraically as well. That concludes our look at the gradient of exponential functions. It is a theme that we will be picking up again though in the next video.